the effective values or the RMS values, root, mean, square. Our book defined the effective value of this sinusoidal voltage is its measure of the effectiveness of a voltage source in delivering power to a resistive load. The effectiveness of a voltage source in delivering power to a resistive load. Now, the way we calculate the effective value, we call that I effective, V effective, whatever you're trying to find. It's always the square root of 1 over t, the integral of over a full period, 0 to t, of the current squared dt. And if it's a voltage, still the same equation. It's 1 over t from 0 to t, v squared dt. That's how we calculate the value. Now, I don't know how many of you took tech math. In tech math 1, we used to write a function like this. Y equals A cosine WT plus phi. I teach that actually, chapter 10 in our tech math book. I teach that on Monday night. I can look at this function, tell you how high it's going to go. It's called the amplitude. The amplitude, how high, is defined as the square root of A. I mean the absolute value of A, not the square, sorry. The absolute value of A. I said the wrong thing. The period, it's defined, it's always as 2 pi divided by W, whatever W is. And we give it the letter T. That's the period. 2 pi over W. And the shift, the phase shift or displacement here is equal to, we used to call them B and C here. It's negative phi over W. And if it's negative, you start on the left side. If it's positive, you start on the right side of the y-axis. I'm interested in the period today, 2 pi over F. So let's look at that. Let's take an example. Let's say you have a sine function for the current. Let's assume for this example the current has let me use the green here. I as a function of time has some maximum value. We'll call it I sub max cosine WT, and it has a phase shift. And I want to find the effective value. That means, in this case, my period, T, if I look at that, is equal to 2 pi over W. It's always 2 pi divided by that number. Now, I want to find the effective value, I effective, RMS value. Well, according to the definition in our book, it's 1 over t, it's the square root of 1 over t, the integral over a full period of the current squared dt. So if I plug it in here, leave t the way it is for now, I'll change it in a minute. And I is this value. If you square that, you're going to have what? I squared m cosine squared WT plus phi. I can factor that I squared m outside. And when you take it outside the square root, what are you going to have? One of them. Well, I'm going to put the t now. I'm going to leave the t inside. T is what? 2 pi over w. You know what? Let's leave it as t, actually. It makes my life easy. I don't have to put 2 pi over w. Leave it as t for now. And how do you integrate the cosine squared? Think about Calc 2. How would you integrate cosine squared? Ignore circuit. If I came to you and said, hey, can you tell me what the integral of cosine squared t dt?
You could do the, what is it? I don't even know what it's called. When you multiply two things.
Cosine times cosine?
What's that thing called again?
Not the convolution.
No, never mind. I don't remember what it's called.
Product rule? Well, that's for derivative. Not integration. Not for integration. There's no product rule for integration.
The uv minus integral ud. Yeah, that's right.
Integration by parts, you're thinking.
That kind of wouldn't work.
Not here. You have to use a trig identity. We have a trig identity that says cosine squared t equals 1 plus cosine twice that number divided by 2. Remember that trig, and if it's sine, will be 1 minus. So if I plug that in, back into this one, I'm going to have, I can take the 2 in the front, put it right here in the front. 1 plus cosine twice that number. Twice that. Again, when you integrate a cosine function over a full period, you will end up with a 0. So if you break it down to 2 integral, the answer to this piece is going to be 0. So what's left? It's really I sub max 1 over 2t, the integral from 0 to t dt, or 1 dt. The other piece is going to have an integral of 0. I'm not going to waste my time on it. That's a cosine function over a full period. So that will give me a t here. And t is going from 0 to t. So when you plug it in, times t, what will happen to the t's? Cancel. So this will be I sub m over the square root of 2. You take the peak value divided by the square root of 2, which is actually ends up being 0.707 I sub m. So when you're in the lab now, when you go to the lab, hopefully this week or Monday, Tuesday will be Monday's schedule. So when you go to the lab on Tuesday or on Friday or next Wednesday, and you take a sine wave, and if you decide to measure that voltage across that sine wave using your digital multimeter, if you put a 10 peak value, if you have a sine wave, let's say 10 volts peak to peak, that means this is 5, this is negative 5, 10 volts peak to peak. And if you use the DMM to measure that voltage, guess what you're going to read? You're not going to see 5 volts. What are you going to see? You're going to see actually 0.707. I said DMM, that's the digital multimeter. That one that has the white, the black, and the red dots. You can use it to measure voltage, current, and resistor, and all the stuff in it by flipping them. Remember that box? When you use that, that should give you 0.707 times the peak value, which is what? 5. And that's what that's going to give you.
That's what they'll give us for the voltage?
Whatever that sine wave is, voltage or current, whatever that wave is. If it's a voltage, we'll give you that number. Because it doesn't give you a sign, it just tells you what the number is.
So it'll give you a steady value?
Yep. And you should see 3.53. So that's what it's going to give you. It gives you the RMS value. Now again, remember, if this is like if you apply this to a resistor, the power is what? It's V squared divided by R if this is voltage. So you're going to square that. What happens when you square that? When you square that, that piece actually will look like this, becomes a positive. And you need to calculate the area under that. So what this one is giving you, what constant value that if I multiply this through it will give me the same area as if I did the whole calculation. And that number for a sine wave is 0.707 of the peak value. So the RMS value or the effective value for a sine wave is always the maximum value divided by the square root of 2, or 0.707 of the peak value. Now, if it's not a sine wave, then that's not the answer. By the way, this value also, if this is current, what's the power? I squared times R, right? So when you square that number, what will happen to that 2 in the bottom?
It'll become 2.
It becomes 2. That's why it's called the half power. That's the half power, because that's a 2 divided by 2 now. Now, let's say you have an ugly looking one. Let me go in the back of the book. It's not a smooth one. If I don't have one, I'll make one up. Here is one. Let's say we have this function. I'll give you an ugly one. And it repeats itself. It looks like this. This is -1 here. This is 1, the peak value. This is 0.1. This is 0.2. This is 0.3. 0.4. 0.5, and so forth. You get the idea, I think. Where does your function repeat itself? Right there. There's your full period, up to here. That's your period. It repeats itself. So to find the RMS, let's say this is current, I don't know, or voltage. Let's say this is voltage. What is V effective? The definition says is the square root of 1 over t, the integral from 0 to t of V sub t squared dt. What is my period equal to here? 0.3. So 1 over 0.3 second. That's a 0.3 millisecond. My mistake, millisecond. So this is 1 over 0.3 millisecond. the integral from 0 to 0.3, the voltage squared dt. One divided by 0.3 e to the negative 3. 3 and some change. And now to integrate that, I got to break it down, right? I got to go from where? 0 to 0.5. 0.05, I think. Not 0.5, 0.05. And what is the equation for that? That's a straight line. So the slope is what? It's negative. The rise over the run. The rise is 1. And what's the run? 0.05. So 1 divided by 0.05 is that negative 20t. The y-intercept is 0. Plus, from here to there is 0. I don't have to worry about it. And what about from here to here? That's from 1.5 to 2. And what's that function?
Bring it up a little bit.
What's the equation for that? Doesn't have a slope of plus 20? But that's not enough. I need the y-intercept. Where does it intercept the y-axis? So every time you go 0.5 drops down 1. This is a minus 1. This is a minus 2. Is that a minus 3? Is that what you got, minus 3? That's minus 1, minus 2, minus 3. And now I got to go through that and figure out what the answer is. It's not going to be 0.707 times the peak value, I guarantee you that. Remember, these are milliseconds here. So it's going to be from 0 to 0.5 milli. When you square that, is that 400t squared? dt plus from 1.5 milli to 2 milli, 20 squared, that's 400 t squared, minus 60 minus 120t plus 9, is it? dt, FOIL method. Oh, 5. Yeah. 0.05. This one? This one?
Yeah, it's going to be 0.15 million.
1.5 to 0.2. 0.15 milli to 0.2 milli. Point 0.15, not. I hate when they use these stupid numbers. Now let's integrate that one. This is 400 t cubed over 3 from 0 to 0.05 milli. Plus, let's integrate that. 400 t cubed over 3 minus 120 t squared over 2, that's 60 t squared, plus 9t, and it's going from where to where? 0.15 milli to 0.2 milli. All of that times that number. I'm getting tired of this problem.
So for the c value, we just assume it would be 0.
Definite integral, right? There's no c.
Oh, okay, then you minus c.
Yep. 400 times 0.05 milli EE, negative 3 cubed. Oh, this is fun. Where's the power? Power of 3 divided by 3 if I get this one right. I'm not optimistic about my pushing buttons here. I got 1.667, which is what, 5 over 3 times 10 to the negative 11, that's for this piece, plus, that's not fun, the last one. Let me go to graph. Where's graph here? $400 x to the power 3 divided by 3 minus 60 x squared plus 9x. Where's my table now? Graph table. Table list. So let's try I'm going to go into ask mode so I can put any number in it. Go to table. When I plug in 0.2 milli, 0.2 EE to the negative 3, the answer, that number is not right here. I get the number for this, 0.0017976, minus when I put 0.15 EE to the negative 3, the answer to that 0.00138487. That number does not make any sense. Let me try it again. The first number. Quiet, people. Table. No, Y, graph. Delete, 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 delete. Okay. Table. Now let me try that number again. 0.05 EE to the negative 3. 1 point, yeah, that's correct. So this is correct, actually. So now subtract these numbers, add to it this, and multiply the result by 3333. Take the square root of that, and we are in good shape. 0.001796 minus 0.00138487 equals, that's this piece. Add to it 1.666666667 EE to the negative 11 is this whole thing multiplied by 3333.33333. It is the square root of roughly 1.5496. So what's the square root of that? And I came up with 1.223. So the RMS value for that problem is 1.223.